That's the game we just talked about.
At the sunset hour.
The one with the yoga mats, like, your animals, bro. Laying down and like, if they had like a weight at their yoga. Pretty good. Like, okay, I'm like visualizing this right now, like. I don't know, I like locked in. I was just.
Applicable. So, yeah, we, there, and you realize that every time your muscles put a force, apply a force to your skeletal structure, that creates a back force in the joints, which can go in the legs. Okay, so we're looking at this belt driving a compressor.
She's over not.
Belt on one side,
I told them she was.
belt on the other side.
Cause it's like.
And so then, of course, we have torque.
So. I don't know if I believe that.
Hold that way, and one, not tension.
Yeah, no,
Finger tension.
you wish you could give the tension in. And I said, I would have one
Oh,
every day.
that would be so much fun.
I would have one every day. For you. What's up?
There's a radius of the pulley. Then the perpendicular force driving, and of course your torque one. 45 newtons equals to 27 newtons. So of course we said that's going to drive the system this way. Okay, now. R that's going to be 0.073 meters. Okay, so work done by the belt on the compressor. Okay, so we go back, remember that word is going to be torque on the system. Theta. Okay, the torque on the system. So if you look at the radius and the perpendicular force vector. Because it's perpendicular force, that theta is 90 degrees, so we're going to get R multiplied by perpendicular force. We want to keep in mind that this is going to be net perpendicular force. What do I mean by that? How do I figure out the net perpendicular force? Right. What are we doing? What have we been doing?
Add them.
Yeah, sum of forces.
Okay.
That's going to give us newtons. And so for every little or infinitely small distance around that cylinder, the perpendicular force is going to be equal to 18 newtons. So each perpendicular force. Okay, so then your work. So torque is R times perpendicular force delta theta. Then of course our R is 0.073 meters. Perpendicular force is 18 newtons. And what did we say our delta theta was?
90.
Or a whole circle.
Yeah, whole circle, which is what?
2 pi.
2 pi. That's gonna give us 0.26 joules for the work energy. That was a nice, simple little problem. Can we make a, can we make a problem that's more fun?
Very different definitions.
Okay, more fun for me. Yeah, I know, but I always equate like harder problems with fun for me, because then I, you know, from everyone in the room, I get that collective, okay. Now, rotational equilibrium. So here's a question, what are the conditions for rotational equilibrium?
Have to equal 0 and some forces.
What are your conditions? Well, 4 to 7 torques to 0. So those are your equilibrium. So when you have a system that's in equilibrium, you always want to make sure that you're adding up to 0, because equilibrium means it's not, well, it's either not going to be moving or it'll be moving at a constant velocity. So what's missing? What is 0 in an equilibrium system?
No change in energy, no acceleration.
Acceleration. So no acceleration of any kind. So, and yes, no energy coming in from outside of the system.
Like,
Okay. So we have a uniform ladder, mass 10 kilograms, length of 3.2 meters. It leads against a frictionless wall, so you better hope you have some friction on the ground or you're going down. If the ladder is not to slip, what needs to be the minimum coefficient of static friction between the bottom of the ladder and the ground? We're just taking a whole bunch of chapters and rolling them all into one problem. Woohoo!
yeah. Fun.
And seeing as how you only have one more semester before you go up to veterinary school, I've decided, let's try to break you this semester, so your whole last semester is just you in like the catatonic state.
I'm already done. You're good. You don't gotta try no more.
Get a betting pool on how long until you're a vegetable.
Yeah. My brain came pretty off of.
All day.
Do what?
I said, you're really turning on your bounce all day.
I mean, isn't that what we usually bet on in our society?
Wow.
Every single sporting event, aren't you betting on someone to lose?
True.
I think it's comparing to a sport, but he's crazy.
I'm gonna gamble if I make it.
I mean, that's what happens in scientific grad school. You end up, I mean, you either go crazy or you leave a sociopath. It's one or the other.
How is that much different?
Well, if you just go crazy, you can still care about people in the world, or you could just lose all emotional connection to things. You're like, Let's try to draw a diagram for this. Okay, So our ladder is gonna lean against the wall. Okay,
You're making me scared.
we have X and Y. Okay. The ladder at the length of L, since it's a uniform ladder, where will its center of mass be? In the middle. So so your symmetric ladder here has its center of mass right in the middle. So when you think about gravity pulling down on the ladder, it's going to come straight from that center of mass. There's the weight of the ladder coming from the center of mass. It's some angle phi. So doing down here. With our angle theta. Now, let's take into account that we have. What do you think that is?
The normal.
Of what? Yep. Normal force of the wall. It makes, what is the angle of the normal force of the wall makes with the ladder?
Is it?
Theta. So we know that. Yep, alternate interior angles. And then down here at the bottom, you're going to end up having static friction force that keeps the ladder from slipping. Then for our system, we're going to consider this a pivot point right down there at the base of the ladder. We have that distance of 1.5 meters from the wall. Okay. Pretty straightforward diagram. The length of your ladder is 3.2 meters, so we'll just make note of that. Oh, and then there's one more. What's that one? Normal force of the ground.
At the pivot point.
Well, because when you think about all these different forces on the ladder, the further you, like if you went up to the top of the ladder and started applying forces, it's going to pivot back and forth as connection to the ground. You can't pivot in the middle because that's in thin air. It's not going to pivot on the wall in the Y direction because that would be anti-gravity. Any pivoting that's done by the ladder is going to have to be done at the base. Now, if you could make that spot on the wall a pivot point, write an article, you'll probably win a Nobel Prize because you found some kind of technology that can basically change dimensional analysis and you've eliminated gravity.
Summer project.
Summer project.
Honey, you solved that.
Yeah, you're just gonna knock that out this summer.
Yeah, amazing.
Take a few weeks, develop anti-grav, be fantastic. Okay. Okay, so let's start thinking about all the things that we're gonna need. We're gonna need to know what those normal forces are. Let's start with our sum of forces in the Y direction.
No, that's all right.
The normal force due to the ground, positive, minus, weight of the ladder equals 0. The normal force for the ground is going to equal the weight of the ladder. Okay. What forces are we summing for the normal force due to the wall? Yeah, it's not the y direction, it's what direction? Mhm. What's the other x direction force?
Static friction.
Mhm. Okay. Now. What torques are going to come into play here? Is the normal force due to the ground going to be a source of torque? I mean, you could model it as such, but what happens?
Just zero.
Yeah, why is it 0?
It's the equilibrium.
Well, let's look at it. What if we did the torque from the normal to the ground? Well, we know that torque F. So this would be R, normal force to the ground. Well, let's see. We'll just call it some sine of some angle alpha between that normal force and the ground. Why is that the case?
The point,
At the pivot.
It's at the pivot point, so R is 0. So you can model torques at the pivot point, but they're all going to come out to be 0.
Just the wall.
So we need the wall and what else?
Friction.
Not friction.
the weight of the ladder.
Oh.
Yeah, the weight of the ladder. Okay, so let's see. Okay, so torque for the normal force due to the wall, that's going to be normal force due to the wall. What's R in this case?
Length.
The length, so L times phi. We have that angle phi between well, no, wait, not phi. Sine of theta. That's the angle. Theta is the one for the normal force due to the wall. Phi is for the weight of the ladder. Now, is this positive or negative? I placed a positive XY direction on there. Is that going to matter for this?
No.
Why doesn't it matter?
It's from the pivot. It's not.
Yeah, which way,
The movement.
rotational motion, which way is positive, which way is negative?
Positive is counterclockwise.
Counterclockwise. So, so the normal force due to the wall, which kind of rotation would it create? Right, because it creates a clockwise rotation with the ladder was to move. So if you look at the pivot point of the ladder, and that normal force due to the wall, if it causes the ladder to move, it's going to go clockwise.
Oh, because it's.
Now we need the torque. Of the weight due to the weight of the ladder. And that's gonna be. Okay, we need something for R. R is just a generalized distance. This is a symmetric ladder, so R is what, so how long is R? Anyone else get it? Where is the center of mass of the symmetric ladder? Right in the middle, so R would be what? One half L. And of course, this one will be positive, because if the ladder was to rotate based off its weight, it would be moving in a counterclockwise direction. Are you okay?
The wall. Okay. No.
Cause the force and gravity's going down. so-
Yeah, imagine there was no wall there, the ladder's gonna fall in a counterclockwise motion due to the weight.
Okay.
Okay, now. But we have a problem. Look at the, let's see. We actually don't know what phi is. We don't know phi. Can we figure out one of the angles? Yeah, how?
Figure out using sine, cosine.
Right, well, so think about this. We could figure out theta by using sine,
Okay.
because, oh, no, wait. Yeah, cosine.
Okay.
Because we have the adjacent side of 1.5 meters, we have the hypotenuse L, we can figure out theta, but we don't know pi. How do we feel about our trigonometric identities? Okay, so phi. Let's figure that out.
Like, if we draw that down, is that like, and we create like its own little triangle, could we
Yeah.
do something like that? And then,
You can, but how do you figure out phi?
There's a lot of people-
So let's just draw that little triangle.
do you see the little?
I know what you're talking
Yeah, I don't,
It's just.
I wonder if we could just use that. If we find theta, then we have the 90, right, and then we just.
Yeah.
Let's see.
We'll put the weight of the ladder there. Continue that down.
Yeah.
That's phi. That's theta. How do I find phi?
Sig beta, and then add that plus 90, and subtract that 180, right?
Yeah, so. 80 degrees. minus 90, Yep, okay. And that's gonna be 90 theta. So now we have,
I don't even know you.
we can put that in for phi. What is that identity? The sine of 90 minus theta is what? Think of it as in the phase shift of a wave. If I phase shift a sine wave by 90 degrees, what do I get? Nope.
No. Cosine.
Cosine of theta. I get the cosine wave.
Good guess.
Did you just guess that
What
one?
did you just say?
Well, they just switch around every now and then.
Yeah, so,
Cosine.
so two ways you can look at it. You can remember the identity that's the sine of 90 minus theta is cosine of theta. Or you can think of it as phase shift of a wave. Because if you phase shifted a sine wave by 90 degrees, you'll get it to line up as a cosine wave. Just think about it. The sine wave is 1 at 90 degrees. The cosine wave is 1 at 0 degrees. So if I shifted that 1 from the point from 90 to 0, that's a phase shift to 90 degrees. That gives me my cosine wave.
So I'm literally just phase shift, do you mean I'm just moving
Yeah,
the
you're-
peak or
Yeah,
trough?
like either, yeah.
Okay.
You're just moving it over by a certain number of degrees.
Sick.
We practice with the extension. Like, what the fuck? Wait, who?
Okay, so now we have these two torques. So now we're gonna say. Okay, so. Some of my torques. Equilibrium system, so that's 0, we already know. That torque is 0. Because the normal force due to the ground is right on the pivot point. Okay, so. The torque due to the normal force of the wall. And the torque due to the weight of the ladder. And let me draw that as a small W so we don't use it with words. Okay. And so what we need to do is we're going to solve this. So what are we going to solve for? So let's go back up here and think about it. What do we want to solve? Because we're trying to find the coefficient of friction. So which one of those do we want to solve for? Normal force of the what? Wall. Because that will directly equal the force of static friction.
Oh, yeah.
And so then remember from there, your force of static friction is your coefficient
It's like.
multiplied by the normal force due to gravity. Or the normal force at the ground. So, okay. Okay, so we're gonna have. Go ahead and do that. Now, let's see, we see that the L's can divide out. We're gonna multiply through by 2. Other way around. You want to solve for that normal force. But we're not quite at the full derivation yet. We had hoped we would get to sine over cosine because that's simple enough. What is cosine over sine?
Is it? 1 to the negative?
Nope,
No.
It's like,
Oh, wait, it's just theta.
not arctangent.
Is it just theta? No.
Nope. Sine over cosine is tangent. Cosine over sine is what? Well, so yeah, I mean, so you can write it like this.
Oh.
But what is that?
Inverse tangent.
But no, so that's more like your, so the
Cotangent.
one with the -1, that's your arctangent. But this one's a little different. So your 1 over tangent is your cotangent. How long has it been since you've used cotangent in derivation?
Probably like almost never.
it's probably,
Now, the problem with this, look at your calculators real fast, find the cotangent button.
Can't.
Yeah, there is no cotangent button.
Yeah, you gotta create the thing.
There was a cotangent.
So what would you have to do to calculate cotangent on your calculator?
You have to put in the cosine.
Yeah, 1 divided by
Yeah.
100. So that's what you would have to do with your calculator. That would be the calculation you put in your calculator. Okay, so that is gonna be,
Strike Harvey.
it's like you're lying on a therapist's couch and it's like,
Strike
you
Harvey.
need to realize that Shrek Harvey cannot get you. Shrek Harvey doesn't exist.
I'm afraid of Strike Harvey.
My
Could have
goodness.
been somebody's Halloween costume.
They made Sour Patch Kid fights and they were just the head.
It's messed up.
Now, we talked about the weight of the ladder. Let's look at the numbers we have in the problem. How are we gonna calculate the weight of the ladder?
Mass times acceleration.
What acceleration? Gravity, mass times gravity, 10 kilograms.
Nobody.
Ooh, but I need theta. But how do we say we would find theta? Let's go back up to our original. So you see our triangle there? Our original triangle? So we're gonna find theta how?
We don't know,
Cosine of what over what?
friction. And,
No, let's use a triangle.
oh, the length and the distance from the wall.
Right, so your x value over the length. So theta. So what that is, 1.5 meters over 3.2 meters. Theta is gonna be 62 degrees, and now we can put that as a problem. Normal force due to the wall is gonna be 26.1 newtons. We have just a little bit more to go. We found out that your static friction force equals this normal force due to the wall. Static friction is the coefficient times what? Which normal force?
The ground.
Which, let's see. Normal force due to the ground. That's just gonna be the weight of the ladder, so mass times gravity. So we found it there. So, so when we do mass times gravity, we get about, so we found this one is 26.1 newtons. Your mass times your gravity, would give you 98 newtons. Your coefficient of static friction, 0.266. Anything less than that, your ladder's gonna slide. Now, in reality, the wall would also have friction. But this problem was long enough. We don't want to start adding the friction of the wall into the mix. Why do you keep repeating that? You just keep saying it over and over and over again.
But she's been staring at.
Are you?
She has issues, okay, we'll talk about it.
Fred Martin?
No, peanuts.
Oh, yes, yeah.
Super racing.
Yep, the Burton. I just figured you would feel like this by this point. Are you guys super duper for real right now?
Didn't realize I was being,
I know.
Orange's face.
No, this is an actual noun.
Oh.
Martina.
It's funny.
No, but that's not the toe.
He's like the best kind of chaos ever. You just kept calling him gangster Pete.
Peanut.
Why gangster?
Looks like a gangster. Gangster peanut.
That looks more like a skateboarder hat.
Gangster. Skateboarders are bad.
No, they're not.
Right, Brandon?
Okay,
This side.
so. We have a uniform beam, weight 196 newtons, length of 1 meter, attached to a hinge on the outside wall of the restaurant. Cord is attached at the center of the beam and is attached to the wall, making an angle 30 degrees with the beam. The cord keeps the beam perpendicular to the wall with a tension of 620 newtons. Now there's a sign of mass 5.8 kilograms hanging at the end of the beam. What is the vertical component of the force exerted by the hinge when A, setting the net force equal to 0, and B, using a torque, so then figuring out the torque. So basically you're doing some forces and then your torques. Okay. We have an idea of what this setup looks like. I appreciate your honesty. You have the wall
Perfect.
and the beam
I was like, that's all I need.
that comes straight out, so it's perpendicular to the wall. Okay, we're gonna have a cord. Oh,
This was just made into a power. And this one's.
it's like a pole on the wall.
Like maybe one of those things that hangs above the.
Yeah.
Or something.
Yeah. So then you have the cable here.
Maybe like that.
There's your hinge. There's your sign.
Yeah, yeah.
It's gonna hang from the end of the beam. There's the sign. So when we're thinking about torque, I mean, we can see that the cable is gonna provide some torque, the sign's gonna provide some torque. But we still have torque if none of those were there. Like, let's say the the cable wasn't there and the sign wasn't there, and you just had that beam on a hinge. Would it stay out or would it stay down? Yes, it's the beam. If you take into account the weight, where is it gonna be? It's gonna be centered at. Why? Uniform, so the center of mass, right in the center. It's symmetric. Center of mass, right in the center. Go right there. The beam. Now, let's see. Our angle theta is there. And so all of these things are happening, and it's gonna exert a force at the pivot point. We need to figure out if that force is up or down and what its magnitude is.
To the point where the hinges are.
Yeah, that's where the hinge is. There's gonna be a force, so the hinge is attached to the wall, the beams and the hinge, and to keep it from rotating, that hinge is gonna supply a force. We need to figure out the magnitude of that force and which direction it's.
So it's like making up for whatever the B doesn't. It's like being.
Yeah, so the sign's gonna try to cause a rotation while stopping that. But we can't necessarily go up or down right now because we also have to force it based off the cable. Okay, so then we also know. This is the 1.0 meters. What, pray tell? Is that distance?
I don't know.
If we were not already in the basement, I might defenestrate you for that comment.
There's windows out there. You can
Yeah, how good is your vocabulary? Question. If a professor was to defenestrate you, which office would you report them to?
You'd be dead.
To do what?
If a professor was to defenestrate you, which office would you report them to?
What does that
Please, I don't know.
To finish?
The office of defenestration? Yeah, it's the office of defenestration.
Answer. Answer.
It's a good one.
You have to remember what defenestrate means.
The nurse's office.
Let's just say you can defenestrate yourself.
So.
First, if they-
Appropriate. Rope someone in. Oh.
So it's what?
Throwing yourself out.
Throwing you out a window.
Oh my gosh, wait, I remember
Can you,
teaching me
if
that.
a professor did that to me,
I'd say thank you.
I'd be dead.
I'd say thank you.
Depends on how high.
I think I'd say thank you and bake a cake.
Yeah.
Might not be going anywhere.
Financial aid.
Depends on which professor.
I didn't die.
That's
Okay.
I'd be like, you didn't do.
See, if it was you, I'd say thank you. If it was Soto. I'd call the police. Strong hands.
Don't forget to incorporate the tension cable. Okay, so let's also remember,
Where's eval? I have like this much written.
go ahead and draw a triangle using the cable.
Cause they're every 2 weeks. Yeah, well, let's take
That's
this
your
one.
tension.
Then our last test is final.
We have Ty and Gx. We'll need that eventually. Okay, so just looking at this, the force at the hinge, do you think it's gonna be a force in X or Y? Remember that sign, everything else on there, the tension, the sign, they're all trying to cause rotations. So the force at the hinge has to be which direction, X or Y? The Y direction, because it's counteracting all the other forces trying to cause rotations. So for part A, we're gonna say sum of forces in Y. Well, the force at the hinge, we're just gonna call that force Y. Let's see,
I will forever.
tension in Y.
I can't read this.
Well, the weight of the beam,
TY, thank
weight
you.
of the sign equals 0. Okay, so we'll pick it up here next time and continue solving this problem. Oh, yeah, if you can wait the beam way to the side.
I like that.